Good morning to everybody. Thank you for allowing us to share our work on firework emissions in Metro Manila during the 2019 New Year. So I have here a photo of two events. The first one on top is actually showing the extent or the visibility degradation to around just 30 meters due to the firework emissions 2019 New Year. And the photo below that is like a normal evening where you can actually see till maybe 70 kilometers away. The list at the bottom in the institution show the collaborators and collaborations of this work. So to provide the context, Southeast Asia, where the Philippines is rapidly developing. There's limited data on aerosols and its interaction with clouds. Thus, there came this study called the Cloud Aerosol Monsoon Processes Experiment. It shows the scientists who are actually in the Philippines who did airborne data analysis, collection and analysis in 2019. They wanted to study more tropical meteorology in its interaction with aerosols. However, before that, 1 year before that, there was a surface observation made by the University of Arizona researchers with Manila Observatory. They wanted to try to analyze what is the background aerosol in Manila, which is in the Philippines. So you can see on the lower right, the status of Manila air, which is on a polluted day, so it's quite polluted, and on a clean day, so just for comparison. The motivation for this work is that on top of this already polluted air in the Philippines, there's actually an extreme event every year that happens during New Year, which we're all familiar with due to fireworks. There's currently no comprehensive measurement of aerosols in a megacity in Southeast Asia where the Philippines is as compared to other regions in the world. So Asia has been known to have the highest firework emissions among the whole world, contributes to chronic health and short-term health problems, can affect clouds and ecosystems. So that's our motivation. In order to understand more the effects of the firework emissions, we have to try to understand the size and composition of these firework emissions. So what the study wants to do is try to understand the sizes of the, in particular, water-soluble emissions of fireworks. What are the particular tracers that are attributed to fireworks? And what are the effects of these firework emissions on the optical properties? So in order to do that, we had two sort of monitoring things. So first we wanted to look at the actual particulate matter samples and their sizes and chemical composition. So we used what they call Moody samplers on the left side with a 12-stage cascade impactor. So these cascade impactors had 12 filters. Samples were collected before, during, and after the firework event. After the firework event, they were extracted in water, and then they were analyzed for ions on the right-hand side using ion chromatography, lower right hand, and for elements using ICP-MS. This is how the filters look like. So these are filters from a typical day in Manila Observatory, 12 stages. So, note that in the size 0.18 to 0.32 micrometers, it's very dark. So typically there's a lot of black carbon in that very small size fraction. So for the firework event, so I'm showing you the stacked elemental water-soluble ions for before the firework on the upper left and during the firework on the lower left. So these are size-speciated, size-resolved distributions. So I emphasize in blue the concentrations where sulfate and potassium are mostly in between 0.18 to 0.56 micrometer cut point diameters. However, during the firework, they sort of shifted a little bit to a larger size range. And as you notice on the y-axis, the concentrations almost multiplied by 10. Nitrate, chloride, and magnesium were in coarser size fractions before the firework and went to finer size fraction during the firework, also with increased mass concentrations. So as you notice, most of the elevated concentrations during the firework occurred between the accumulation range, or so these are the sizes between 0.32 to 1.8 micrometers. This actually has implications on health. So the lower right side shows the deposition efficiency of particles going into the respiratory system. So the larger the value is, the more they're able to go into the lungs. So the bottom side shows the size or diameter, and you see that the yellow portions are the sizes of the firework emissions that we've seen that were enhanced, and means that these particles are actually able to go deep into the respiratory system. Because the things that we collected are water soluble, we saw that these water soluble mass concentrations were enriched 5.7 times. And actually this fraction to total PM2.5 increased by 18.5%. This enrichment has impacts on health because they become more respirable, and environment, clouds, and also how they impact lakes, water bodies. So this is a picture of size resolved enrichments. So the red line shows this size enrichment during the firework emission, while the value in the parentheses shows how much this particular species was enriched during that time. So we can see that the enrichments were actually all similarly in the 0.18 to 1.8 micrometer range. All of these species were actually associated with firework components, or they're called firework tracers. And in the gray is what how they contribute to the fireworks. Sulfate and succinate were not considered firework tracers because they're secondarily produced. Similarly, if one were to look at the size enrichments of the particular tracers, you could see that all the numbers at the bottom show the enrichments in particular size bins. So they were all between 0.56 and 1.8 micrometers as well. In order to try to look at the optical properties of the aerosols due to fireworks, we looked at the data from a Lidar from the University of Wisconsin. So this is the beam of the Lidar, very visible during that time because of the many particles in the air causing the backscatter of the light. So this is the data from the Lidar during the firework activity. So for 48 hours at the same time of the sample collection that we have for the filters. So the red signal, the red color shows higher backscatter signal, which is correlated to higher surface loading. So this occurred around 10 p.m. Of December 31, 2018 until around 8 a.m. of January 1, and was just very, very close to the surface, between 200 to 400 meters. So I divide this into two portions because I want to show that in this first portion, between 10 p.m. to 3 a.m., this high aerosol loading was associated with very high optical depths of 1.1. So this is very high values. And after the firework peak, even if there were still surface loading that was seen by the Lidar, the optical depth became lower. This is a map of, this is a chart of the hourly PM2.5. So from the government that we got, and we plotted it with hourly rainfall. And we see that during the time from 10 p.m. to 3 a.m., the time with the very high optical depth values were associated with particulate matter that were very high, 400 micrograms per cubic meter. Note that the 24-hour PM2.5 guideline value of the Philippine Clean Air Act is only 50 micrograms per cubic meter. And afterwards, you can see that after the peak of the PM2.5 decreased. In summary, during the firework event, water-soluble ions and elements were enriched. They were elevated by a factor of 5.7 or 5.7 times. Most of the fraction was actually due to ions in the submicron size. And the water-soluble mass fraction increased 18.5%. The tracers were all associated with firework emissions, and actually they comprise a very small amount of mass of the total PM 2.5. Thus, it was important to look at the size speciation to be able to see that heavy aerosol loading at the surface would increase to 1.1. So we acknowledge the following funders and people who supported us. And thank you for listening. And if you have any questions.
Okay. Hello, Jen. I just checked Q&A. Uh, Jen? So, Ma'am Jen, while waiting for a question from the participants,
Yes.
would you like to or what are the key importance of the uh, study? Did you
Sorry.
hear me?
Not really.
Uh,
Ooh.
Ma'am Jen, can you hear
Hello.
me? This is Sting.
Yes, I can hear you. Yeah.
Yeah, this is Sting. Can you hear me?
Yeah. Yes, I can hear you.
Okay, the question is from Anna Sergina. Hi, Jen. Great talk. Since these aerosols are water soluble, uh, would rainfall be sufficient to clean the firework emissions? You can
Yes.
you can
Okay. So since
you
they're water
can check
soluble,
the Q&A, Jen.
yes.
You can okay go ahead. Check the Q&A, Jen.
Yes. Oh, Certain.
Can you hear me?
Yes.
Can you check the Q&A box in your
Yes.
screen? Yeah, that's the question of the.
Um,
Hello, Ma'am Jen.
yes.
Did you get the question?
Yes, I already. Rainfall, if it's water soluble, yes, rainfall can wash those water soluble aerosols away. However, if the rainfall is not too much, like if it's a drizzle, the aerosols can actually be enhanced. Also, there's a particular size fraction of aerosols that are not able to be removed by rain. So it depends also on the size.
Thank you very much. Any question please? So if there's no more question, thank you very much, Jen.
Thank you.
Is the next speaker ready?
Next speaker ready. Oh.